Hello, and welcome back to Physics 141 Classical Electromagnetism 1. So, let us review first what we have discussed so far. So, in our previous lessons, we discussed about Gauss' law as a tool to find the electric field for a continuous charge distribution. And we also have discussed about the potential difference, which is just the potential between these 2 points, and it's related to the electric field dot with or multiplied by length dl, that dl. So we will use these two equations for the lesson on conductors. So in this lesson, we will be uh, focusing especially on conductors such as metals. So if you have a conductor and you put a charge distribution in a conductor, how are the charges distributed inside a conductor? So we will first discuss some basic properties of conductors. So one of the basic property, if you have a conductor, is that the electric field is always zero inside a conductor. This equivalently means that there is no charge inside a conductor. There's no charge distribution or volume charge density inside a conductor. And any net charge on a conductor will reside on the surface of the conductor. So take note, even though this is a solid conductor, say if you put positive charges initially at the center of the conductor, since like charges will repel each other, so they will move as far away from each other as possible until they reach the surface. So if you have a conductor, all of the charges, if there is a net charge, then that will only reside at the surface of the conductor, and they will not reside inside the conductor, meaning there will be no charge distribution inside. And if there's no charge enclosed inside, according to Gauss' law, then the electric field inside, the electric field will also be zero. So another property of conductors is that their surface is an equipotential surface, meaning the potential at every point on the surface is the same. And if you are to take, for instance, the potential difference between 2 points in the surface, then of course you will get zero. There's no difference. Another property of conductors is that the electric field at the surface is perpendicular to the surface. So this is just the electric field near the surface or at the surface. Of course, at far away from the surface, this could bend or this could diverge, so it will no longer be perpendicular. But near the surface, it's perpendicular to the surface. So if you have a conductor with a cavity, for instance, a cavity inside, there's a hollow space inside, and for instance, you put a positive charge Q inside the cavity, then there will be induced charges on the two surfaces of your conductor. So since, assuming this conductor is initially neutral, then if you place a point charge Q in the cavity, in the hole, then there will be negative Q worth of induced charges in this inner surface here. And since the conductor is initially neutral, then there will be a positive Q on the outer surface of the conductor. So if you will take note, the total charge in the conductor is negative Q in the inner surface and positive Q in the outer surface, so it's still neutral. It's still zero. The total charge in the conductor is still zero. This also means that the electric field inside the conductor will be zero, because if you take a Gaussian surface here, so since say you are finding the electric field in this region here, in the conductor region. So if you take a Gaussian surface here, the total charge enclosed will be positive Q plus negative Q, which is 0. So therefore, total charge enclosed is 0, electric field is 0. So you must always remember that inside a conductor, the electric field is always 0. Okay. So as an example, we have a point charge placed at the center of a spherical cavity of a spherical conductor. So take note, we are emphasizing here that this is a sphere, because maybe with our drawings just, or our drawing just looks like a circle. So this is a sphere, a spherical shell, conducting shell, so it could be a metal, and you have a spherical cavity inside your conductor, and then your conductor is assumed to be initially neutral, and then you place a charge Q at the cavity, at the center of the cavity of your conductor. So your spherical conductor has an inner radius of A and outer radius of B, and you are asked to find the electric field in all regions. So there are 3 regions here. Since this is spherical, so we will base the regions on their R values. So from 0 to A, from A to B, which is the bulk of the conductor, and then from B to infinity, so outside of the conductor. Okay. So, sorry. Take note that due to the positive point charge here, there will be a negative charge in this inner surface here, induced negative charge, negative Q, and there will be an induced positive Q charges in the outer surface of your conductor. So let's now consider the first region from 0 to A. So from 0 to A, we just use Gauss law. So when we make a Gaussian surface, our Gaussian surface is spherical. And then, of course, Gauss law is originally an integral. So closed integral of E dot dA is equal to the charge enclosed over epsilon naught. But for this case, for spherical symmetry, all points in your Gaussian sphere have the same value of electric field, meaning the electric field is constant in the surface, at the Gaussian surface. So you can take it out of the integral. By the way, this is EdA cosine theta, and in this case, in our Gaussian surface, for instance, in our Gaussian surface, the area vector is along r hat, and the electric field is also along r hat. So the electric field and the area have the same direction. Therefore, ang E dot dA is just EdA. And the closed integral of dA is basically just the area of your Gaussian surface, which is 4 pi r squared, or the total area A, say EA. So basically, our Gauss law equation can just be simplified to this non-integral form. This is only in the case that the electric field and the area vector are in the same direction. So EA is just equal to Q enclosed over epsilon naught. So that is what we have here. So the total area, this is basically the total area, the closed integral of dA, which is just 4 pi r squared. And your charge enclosed by this Gaussian surface, the charge enclosed in the Gaussian surface is Q, positive Q. And of course, you will have, it will just be the electric field of a point charge. So it's in vector form, its direction is r hat, since this is just a point charge. Now, for the second region, r is between A and B. So our r is in this region here. So we make a Gaussian surface in this region, and you will notice that the charge enclosed will be, you have a positive Q here and then a negative Q here in this surface. So the total charge enclosed will be Q plus negative Q. You will get 0. So if the charge enclosed is 0, therefore the electric field is also 0. Which is true because this is the inside of a conductor. The electric field inside a conductor is always 0. For the electric field outside, this is from R is from B to positive infinity. The charge enclosed here will be Q. So this is your Gaussian surface. We make a Gaussian spherical Gaussian surface outside our conductor. So the total charge will be Q plus negative Q plus Q, and that will give you Q. So therefore the electric field outside will just look like the electric field of a point charge. But here, this is not actually a point charge Q here. This Q here is the charge of a surface. This is actually a surface charge density Q here, or surface charge distribution Q. Okay. So let's have another example. Suppose we have a charge conducting sphere and it's placed inside a spherical conducting shell. So in the previous example, you just have a point charge, but now you have a charge conducting sphere, and this is also a conducting shell. So we have two conductors now. This is a conductor, a spherical conductor, and a spherical conducting shell. So say this could be copper, this could be iron, so it could be a metal or any conductor. So your charge conducting sphere has a charge Q and has a radius R. Your spherical conducting shell has an inner radius of A and an outer radius of B. So these are the given. So we are then asked to find the charge density at R is equal to capital R, so in this surface here, and at R is equal to A, so in the inner surface, and R is equal to B in the outer surface of the spherical conducting shell. Then you are asked to find the potential, electric potential at the center. So at this point, at R is equal to 0. And then if the outer surface of the conducting shell is grounded, how will your answers in parts A and B change? So we'll just discuss about, elaborate about grounding in the next, when we go to this problem. Okay, let's first solve for the first problem, letter A. Find the charge density on the three surfaces. So you have three surfaces. The surface of the conducting sphere, this one. So you will note, take note, this is a conductor, meaning this charge Q will only be distributed on the surface of this solid conducting sphere, and there will be no volume charge distribution inside a conductor. Rho is always 0, so electric field inside is also 0. So therefore the charge density, assuming it's uniform charge distribution, the charge density at R is equal to capital R will just be the total charge, which is Q, over the total surface area, which is 4 pi capital R squared. So the total surface area of this conducting sphere is 4 pi capital R squared. So this is the charge density in this surface here. How about at R is equal to A in the inner surface of the conducting shell? So in the inner surface of the conducting shell, since this is a positive Q, there will be induced charges on the inner surface with a total charge of negative Q. So therefore, the charge density in this surface will be the total charge negative Q over the total surface area of this inner surface, which is just 4 pi times the radius, which is A, 4 pi A squared. So this is the charge density. It's actually negative because this is a negative charge distribution in this surface here. Now for R is equal to B, for the outer surface of the conducting shell, for this region here, or for this surface rather here, the total charge will be Q, and the total area will be 4 pi b squared. So the charge density will be q over 4 pi b squared. So again, the assumption here is there's a uniform charge distribution. For letter B, find the potential at the center. So meaning that's the potential at R is equal to 0. So your R is equal to 0, so meaning R here is 0, and our reference, we will use infinity as our reference point. So you will notice that this integral actually has 4 intervals from 0 to capital R. That's the first interval. From R to A, second interval. From A to B, and then from B to infinity. So those are the 4 intervals rather. Now, in the interval from 0 to capital R, the electric field there, say E1, region 1, is actually 0 because that's a conductor. For region 2, we actually have solved this problem. The electric field outside a charged conducting sphere is just 1 over 4 pi epsilon naught q over r squared. So that's the electric field in this region here. For the region here, from A to B, since that's still the bulk of the conductor, so the electric field there is 0. And then for the fourth region, from B to infinity, if you take a Gaussian surface here, the total charge will be Q, it's negative Q plus Q, so the total charge will be Q, and the electric field at region 4 will still look like a point charge, 1 over 4 pi epsilon naught q over r squared, or kq over r squared. So the only contributing intervals for this integral will just be region 2 and region 4, since region 1 and region 3 have 0 electric fields. So there will only be 2 regions with non-zero integrals, E4, region 4, outside of the conductor, and from R to A. So from A, or from A to R, and from infinity to B, or from B to infinity, or from R to A. Okay, so we substitute the value of E4 and E2, these values, in our integral here. Our DL is again radial, so it's dr r hat, and our E2 and E4, the direction of these electric fields are both r hat direction, so you will have r hat dot r hat, that will just give you 1. So of course this is a familiar integral, so you will just have dr and then 1 over r squared, integral of dr over r squared, and that integral of 1 over r squared dr, or dr over r squared, is just negative 1 over r. There's a negative sign here, and this is negative 1 over r, so you will just have an answer of positive 1 over r. So your 1 over r answers of this integral will be evaluated from infinity to b for this integral, and from a to r for this second integral, and that will give you this result. So this is now the potential at the center of this continuous charge distribution. Okay, let's now have the last problem. If the outer surface of the conducting shell is grounded, how will your answers in parts A and B change? So I think you have heard of grounding in your physics 41, right? So when you ground something, you're just basically transferring the charges in that surface towards the ground. So this is the symbol for the ground. So you basically just connect a conducting wire to your surface, so that the charges in the surface can travel towards the ground. So basically that's just grounding. You're taking away the charges on the surface, you're putting it in the ground, or you're transferring it in the ground. So when you ground the outer surface, this positive Q charge distributed in the outer surface will be gone. So therefore there will no longer be a charge distribution on the outer surface, because you already grounded it. So you transfer the charges towards the ground. And if that's the case, then the electric field outside the conductor will become 0, because if you take a Gaussian surface here, the charge enclosed will now be Q, and negative Q, the total charge enclosed will be 0. So therefore the electric field outside will also be 0. Okay, so the charge densities at the surface of the conducting sphere and at r is equal to a will still be the same, but for r is equal to b, since there's no more charge distribution here because you already grounded it, you already ground the charges, so there will be no charge distribution sigma at point r, or at r is equal to b, at points at points on the outer surface of your conducting shell. So for the problem, letter B problem, the potential at the center, so you will notice that in the 4 regions, only one region will now contribute to the potential, because the first region, the third region, and the fourth region all have 0 electric fields, so 0 electric fields, so 0 contribution. So the only contributing integral will be the integral from A to R. So from A to R. So this the integral of this region here, region number 2. And evaluating that will give you this value here. So what will change in your answer will be the charge density in the outer surface and the potential at the center of the sphere. So the grounding has an effect on the potential at the center. Okay, I think this is the last example. Suppose now you have 2 spherical cavities on your spherical conductors. So the 2 spherical cavities have different radius. One spherical cavity has a radius of A, and you place a point charge QA in the first cavity, and in the second cavity you place a charge QB. The second cavity has a radius B. Okay, so the questions are similar to the previous problem. Find the charge densities at the surface, this surface here, this surface here, and at this surface here. So we have 3 spherical surfaces in this case. And you find the electric field outside the conductor, so outside the conductor and within each cavity. So there's only 3 electric fields that matter. The electric field inside the conductor in this green region here is 0 because this is inside the conductor. So the electric field within this cavity, and outside this conductor. So that's for letter B. And lastly, what is the force on QA and the force on QB due to the charge distribution? So for the first problem, at A, or at the first cavity, the surface charge density in this surface is just the total charge over the total surface area. So the total charge will be there will be negative Q here. Since this is a positive charge, there will be negative QA induced charge in this surface, and the total surface area is 4 pi a squared. Similarly, for the second cavity, there will be a negative QB worth of charges induced in here, so negative charge densities here. And for the surface of the conductor, outer surface of the conductor, since you already have a negative QA induced here and negative QB induced here, there will be a positive QA plus QB induced in the outer surface of the conductor. So the charge density will be QA plus QB over 4 pi r squared. So essentially, the charge density looks like the total of the the 2-point charges inside the conductor. For letter B, the electric fields outside. So we make a Gaussian surface outside. So this is our Gaussian surface. So the Q enclosed, the charge enclosed by this Gaussian surface will just be QA plus QB minus QA minus QB plus QA plus QB, and you add all that and it's just QA plus QB. So therefore the electric field outside will just be K and then the total charge or charge enclosed QA plus QB over R squared. Okay, how about within each cavity? So within each cavity, so we make this Gaussian surface here. But take note, the directions of the area vector and the electric field of this point charge will no longer be along the r hat direction or r direction. It will actually be along the separation distance vector curly r hat. So in this case, the charge enclosed is just QA, and this will be the direction of your electric field, and the area vector will also be directed along this direction, the curly r or the separation distance vector from the source point to the field point. And how do you get this separation distance vector? So of course you get the r first, the field point position, and then the source point position, and the separation distance is just r a minus r a prime. So this is the curly r a, and the electric field will just look like KQ over R, but it's now curly R, the separation distance vector R sub A. You can do the same for B and you will get a similar result. So, but of course this is not the final answer. You have to expand this first, and I will just leave this on your for you to work out. For the last problem, what's the force on QA and QB? So let's first start with QA. So you will notice that how many forces are acting on QA. So there will be, due to this surface charge distribution here, due to the induced charge negative Q, but you will notice that the force due to the surface here will be symmetric, so they will cancel each other out. Therefore the contribution for this surface will be 0, and then there will be this charge distribution here. So since force is just Q times E, the electric field at that point, QE, okay, I will reveal the answer. So the electric field at point A will just be QA times the electric field at point A. So the electric field at point A will be due to three distribution. This distribution here in this surface, this distribution here, and the conductor itself. So for this distribution, again, the electric field contribution will be 0 because it will be symmetric. For this case here, the total charge enclosed will be QB and negative QB, so 0. So there's also no electric field at this point due to this distribution here. And due to the surface, because since this is inside the conductor, the electric field at this point will also be 0 because this is inside the conductor. So the electric field at this point will be 0. Therefore, there will be no force acting on QA. So QA will be static. It will not move. There are no forces acting on it. Similarly, the same also goes for B. There's also 0 net force acting on B. So that's the end of the lesson. So our next topic will be the last topic of the chapter. It will be on capacitors. So you have already discussed about the basics of capacitors in your Physics 41. So we'll just supplement to what you have learned in Physics 41. So that's all for conductors. So basically, there's 0 electric field inside the conductor. There's no charge distribution inside the conductor. And if you ground a conductor, you're basically getting all the charges on the surface. There will be no more charges on the surface of a conductor or grounded conductor. Okay, so that's it for this lesson, and I will see you next meeting.